All right, good afternoon. Let's get started. Okay, so last time we were talking about the VM diagram. So we went over 2 examples. So here was the last one, right? So today we'll continue do more VM diagram together. All right. So last 2 problems. One was a cantilever beam, and then this one was a simple beam, right? I think we'll do one more simple beam, and then we'll move on to look at another example, overhanging beam. And so this way you can see all different beams, and also hopefully we'll cover different loads: distributed load, concentric force, and concentric moment. All right. Okay. So here's another example here. So we have this simple beam. Can you all see the numbers? The load P is 40 pounds, all right? And then the distributed load Q there is 5 pounds per inch. Okay, so the unit you can actually just say treat it as meter, Newton meter, right? It's similar, just different unit. Okay. Somehow this picture, I like this picture, so I use it. But the unit is not the way I actually like. We want to use it SI unit. Okay. Hmm? Newton, Q will be Newton per meter, okay? Right, moment will be Newton meter, all right? Okay, so for this one, let's say we want to get the VM diagram. We want to figure out how the V change, how the M change, and then find out where the maximum V is, where the maximum moment is. Okay, so to draw this one, remember we have the 7 rules that you can use without make the cut, use the equation of equilibrium. Okay. All right. So step 0. How can we get the VM diagram? Step 0. You draw the free body diagram of the system. Find out the reaction forces. All right. Because if you want to draw the VM diagram, you need the reaction forces. So here is one reaction, RA. There is another reaction, RB. Any other reactions? No, because P in support, right? P in free to rotation. So there will be no reaction movement. This thing can freely rotate. It just cannot go anywhere. All right, so RRB. Now, what's the equation we can use to determine RRB? Sigma Fy equals 0. First one. All right. Okay, so we have RA plus RB. And minus P, that's the 40. Then minus Q times the half L, right? That's the length, and that will equal to 0. Okay, so 2 unknowns. We need one more equation. Moment to A, okay. So how about moment to B? You can always do moment to A, moment to B, right? And in fact, actually, you want to use this extra one to check whether your RARB is correct or not. Okay, let's start with B. Sigma MB equals 0. All right, now translate this equation or express it out. To point B. Remember, we are doing point B. So you have RA, generated moment, right? So RA times the length, that's 80, right? That's clockwise. So we call this positive or negative? Negative, okay, so negative. And then load P, counterclockwise, so it's positive. P times half the L. Okay, then you have this distributed load here. How you calculate the moment generated by this distributed load? In theory, you're supposed to be calculate all the small part, right? Calculate the force. You have a small q times this small dx, and that gives you a force. That force times this distance gives you a moment. Then you integrate. right? Mathematically, you should do that way. But we already did this a long time ago I think in statics, right? When there's a distributed load, how you calculate the moment? I mean, this constant uniformly distributed load. You make it, this was equivalent to a concentrated force here, right? And this force, let's call it F here. What's the magnitude of this force? Should be Q times the half L. That's this force, right? And then this force, as if it apply in the middle, you calculate moment by time the other distance. What's the distance here? 20. So that's 1/4 of the L, right? Okay, anything else? Nothing else. So equals 0. Okay, now can we find out RRB? Yes, okay, let's use this one, find RA first. So you have RA times L. L, that's 80. Right? Plus P, that's 40. Times half L, that's 40. Right? Half L is 40. And then this one here, plus or minus? Plus, right? From point B, it's actually counterclockwise, so it's plus. Okay, so your plus Q, that's 40. 40 times half L, 40. Okay, and then times a quarter L, that's 20. So equals 0. Okay, anyone get a calculator? Or we can just say, eliminate 40, eliminate 40, eliminate 40. Right? Okay, so then we can eliminate another 2. Okay, eliminate another 2. This will become 20. This will become 10. Okay, so what do you have? RA will be 20 plus 40 times what? Times 1, times 10. Right? Have you seen anything? Q is 5. Okay, I got it wrong. Q is 5, right? So this part should be a 5. Okay, so this will be a 5. All right, so you have 5 times 10. Right? So what's RA? 70. Okay, anyone got a calculator? Double check on my calculation. Because if I got this wrong, then everything will be wrong. Right? So you don't want that to happen. Double check RA. Okay, I'll do it here again. Let's see, that's 2A. That will be 40 out. So you have 40. 40, so 220 will be 20, and then this will be 40 out. That's be 5 times 10, so 50. Okay, is that correct? All right, so 70. All right, now we can use the other equation, sigma m a equals 0. You can get from here. You can get RB. What's RB value? Okay, we can try here. So RA plus RB. Plus RB equals to P is 40, so equals to 40 plus Q is 5. 5 times 40. 200, right? 40 times 5. 210? 200. So total is 240, right? Okay, so what's RB? Let me write one more here. So you have RA, that's 70 plus RB equals to 40 plus 200, 240. Now what's RB? 170. Okay, so 170. All right. Okay. So again, make sure you use all the 3 equations. Determine the RRB. Make sure RRB is correct. Right? And many of the mistakes in the VM diagram all come from here. Just get the wrong RA, wrong RB. I cannot emphasize enough how important RRB is, because if this is wrong, everything else will be wrong. Right? That's why I say you need the statics to be able to determine RRB and for this course. All right, let's say RRB now we got it correct. So let's draw the VM diagram. Okay, so this will be V. All right, so this is the middle point. Okay, now this will be the B, the M. Okay, let's draw V. So RA equals to 70. So here is 70. Here is 170. All right. Okay, V, star 0. All right. Okay, once you start 0, what do you see here at point A? You see RA 70. That's arrow point upward 70. So we should jump 70, right? Make force jump. So jump up 70. So here is 70. Now what do you see? Negative 40. Now when you move away from point A, what do you see? That's what my question. Nothing, right? Q equals 0. So V will be constant. Just keep going. Keep going, keep going. Oh, I see a constant force of 40. So what should I do? Jump down. Follow the arrow, right? Jump down 40. So here I end up here. This will be 30 because I'm just coming down 40. Okay. Now next what I see. You see a distributed load, right? So therefore dV dx equals Q. Will be a constant. So you know it's a straight line, sloped line. Right? Going downward. So it will be something like this, going down. Now, where is this point? How much are you going down? How much are you going down? The amount of the difference from point A to point B. What's the difference? It's the area of Q, right? Okay, so from point C to point B, how big is this area of Q? 5 times this 40, 200. So you should go down 200, right? Remember this relation from point A to B, Qx integral equal to the V from point A to point B, right? So you should go down 200 because this Q area will be 200. Now from 30 go down 200. Where you end up? Negative 170. Okay, so this will be negative 170. Sorry, this is not out to scale. So if you have space, you want to make this one a little bit down further. So it can be proportional, right? Okay, now once you're here at point B, what do you see? A constant force RB pointing upward. So I should go up that amount. So go up 170. Now we are in 0. Oh, start 0 and 0. That's perfect. Okay. All right, here is a common mistake. Okay, that often occurs. Remember how we calculate here. We draw this force here. This force doesn't exist. Right? This is just a substitute for that distributed load when you write the equation of equilibrium. So therefore, when you draw the VM diagram, you cannot use this force because it doesn't exist. So the mistake often occurs is instead of draw this sloped line, people will just go this way and then say here, oh, jumping down this amount, and then you get straight line. So that's the wrong one. Okay, so this is a totally wrong approach. All right, so you cannot replace the distributed load as a constant force when you draw the VM diagram because they're different, right? Distributed load, the load is shear, so the gradual change. And if you have a constant force, it's just a sudden change. So these two are not replaceable to each other. All right? Keep this in mind. It's only when you write the equation of equilibrium you can somehow use this way. All right. Now we got the V. Now what about M? Start 0. All right. Straight up or down? up because this is positive area. So you go up, right? Now, where you end at? Here. What's the value here? How much you change from point A to point C? The area above it in V, right? How much is the area? 70 times 40. How much? 2800, right? So this should be 28. It's 70 times 40, so 2800. All right. Now, once you reach here, you immediately see a counter force. Should M jump? No. M don't jump because it's a constant force, right? Force make force jump, movement make movement. There's no constant movement, so no jump. Okay, so now, past this point, you'll go somewhere here, right? Or keep going up or going down. Now, you're going to go up or down? Why go down? So from 2 points, right? From point A to point B, you go up if the area in V is positive. You go down if the area in V is negative. Now the area in V is positive or negative. Let's say from this between these 2 points, from point A to point B, it's a positive area or negative area? It's a positive area. So you should go up. Now, how do you go up? Straight line or some kind of curved line? Curved line, because you're not accumulating area at a constant rate. Now you accumulate at a sloped rate. So at the beginning, you accumulate quicker. So gradually, you accumulate less amount. So your curve should be actually like this. Peak at here. Why it's peak there? That point V equals 0. So you pick up. Now, once you pass this point, now you accumulate this negative area. So you go down. Right? So go down at the beginning, go down slow, and then very quicker later. So what do you have? What kind of curve is this one? Parabolic. Right? So you have one parabolic curve as shown here, and the peak is at this point. So this is the maximum. Maximum. Oh. Okay, that's the maximum point. Okay, now can you determine the value at this maximum point? Yes, because I know I started at 2800, right? 2800. And then I accumulated this much area. So this is the area I accumulate. Can you determine this area? Can you determine this area? Yes, you can determine. Why? Because I know this will be height will be 30. This triangle, can you determine this distance? Let's call this distance, give a letter. Let's say x. Can you determine the x? Yes, because this triangle, you know this part is 170, this part is 30. You have a triangle cover 40. So you can figure out trigonometry, right? So you can just figure out what there. These two triangles are similar, so you figure out the x. Okay, so I leave that to you. Find out the x, then determine the maximum value. Okay. All right, any questions about this example? Okay, if no other question, let me make a comment here. Okay, it's the way actually how I draw it. Okay, in statics, you learn about the equivalent force, right? If you have a force here, what's the effect of this force at this point B? What's the equivalent of this force, the effect of this force at point B? You're going to have the same force move here, right? And you're going to have a moment applying here. Right? Is that correct? Right? Any force, right, applying here to this point is basically a force applying here, also a moment applying here. Is that true? Yes. Okay. So based on this, you can easily, quickly, kind of, or physically look at the picture and find out how to do the VM diagram. Okay. Here's how. If you look at, say, I'm starting from the left, I'm going to the right. Okay. First thing I see is this force here. right? So for this any point here, what do you have? You have this force move to here, right? And a moment to here. Yeah, so that's why if you look at this point here, the shear force should be this one, just move there. That's why at any point here, you have this force just move there. So you have this constant V there. Now if you look at this point, some point here. Now on this surface here, what do you have? You have this RA move there. You have this P move there. And then you have this part of the Q move there. That's why you get this balance. Oh, we join this surface, you get this there. So you can kind of think, oh, all this load on the left, just equivalent to there. That gives you the V. So if you think this way, you can easily calculate the value anywhere. And you can plot it. Right? Now what about M? M basically, if anywhere, let's say you look at here. That M will be RA times this distance. That's why you have a linearly keep increasing. Right? And if you look at it somewhere here, this location, for example, on this side, you're going to have the RA generate movement here, you have the P generate movement there, and you have this part of the Q generate movement there. Okay. So that's basically how you think about how this movement is changing physically, how you do that. And that, to me, is an easy way. Whenever any cross-section, I can quickly find out the movement there. Basically, just count everything here to that surface. That's how you determine the moment at anywhere. All right. So that's just a side note. If you feel you can follow this way, fine. If you feel confusing, just ignore it. All right. Okay. So, any other questions? Okay. So for this one, let me actually change this slightly. Okay, I want to change this one. Okay, well, change to this problem. Okay, everything is backward, but we'll just draw it there. Okay, the reason I want to change this way, because we can kind of use this immediately start. Okay, I want to make it a little bit complicated. Let's say here, we have another moment. Okay, which way? Clockwise or counterclockwise? Clockwise? Okay, let's say clockwise, so that's this way. Okay, give a value. MO equals to 100. Okay. Okay, this is 100. So this P here looks like the value was like 5, right? So we have a force of 5 here, P here. And then the Q was like 4. So this Q equals 4. Okay. All right, so for this one, the length 10 meter long, right? So you have 5 meter here, and then 5 meter here. Okay, so now where is this one? We need to give a distance. How about 2 meter long? 2 meter here. This 2 meter. Okay, for this loading situation, you have constant force, constant moment, distributed load. Now all three are combined there. Right? Cannot be more than this. Or maybe you can have 2 constant force or something more. But it's same thing. Okay. So anyway, here we have all 3 basic type of load. Constant force, constant movement, and distributed load all here. So let's draw the VM diagram, this one. All right. Okay, for this one, because it's a cantilever beam. Now, is there any reaction here? RB here? No. So I know RB equals 0. Right? So immediately, actually, I can kind of skip the step 0 because I can start right away. I know RB at this point is 0. So I can immediately start. Of course, you can still, a safe way is you can still find out what's the RA here. This is the RA. Okay, by equation of equilibrium. So you're going to have a moment here as well. So this will be M up. Okay, let's say we want to draw the VM diagram. We can start immediately. Okay. So this will be the M. This is the V, this is the M. Okay, now draw the V diagram first. Start 0, right? Start with 0. Okay, now once you start, what do you see? You see a 5 pointing down. So you should go down 5. That's here. Okay, next. Nothing here. So straight line. Okay, oh, I see a constant movement. Jump? No, because that's a movement, right? So ignore it, just keep going. Oh, I see a constant, not constant force. I see a distributed load. Now what should I do? So you imagine you have a small load there, right? Gradually, like a lot of small load make pushing you down. So you should go, oh, jumping down, very tiny, jumping down tiny, jumping down tiny. So you keep jumping. So this will be straight line go down like this, right? Okay, then here, what do you see? You see this reaction RA, right? So that will make you go up 0 here. All right. Okay, now for the moment, I think I'm running out of space here because this one is kind of low. Let's see if I can move this some way. So I draw a line. Let's see. Okay, so can I use this page to draw the M? So let's draw the V first, or just repeat it. Okay, so this is the baseline, this is the V. So line go this way, and then here at 5 it go down, so it's this way, right? So that's the V diagram. Here is the 5, and then here, what's this value here? Look at this. Oh. Look at this one. Okay, so here is 4 times 5. That's the area, 20, right? So you go down 20. So you end up. Where is that? Oh, here. Okay, so you go down negative 25 because start negative 5 here. You go down by 20, right? Okay. Any questions about the V diagram? What's that? Oh, not the V. Yes. Thank you. This is the X axis. Thank you. All right. So this is V. Now what about the M? Now we have plenty of space we can draw here. So this will be the M. Okay. How do you draw the M? Star 0, right? Okay. Once you start 0, what do you see? Cross it. You start accumulate this area, negative area, right? Okay, so negative area, so M will go down. So you'll go this way, downward. Right? Okay, so let me draw a little bit less slope. So I go downward. I will just draw here. Okay, so I suppose go here, right? Don't use this one. Okay, now is this correct? No, what did I ignore? Okay, there is a constant movement here at the 2 meter location, right? The movement is this way. What's the value? This way, negative. What's the value? Anyone remember the value? Here. We put 100, right? Okay, so supposed to be a 100 this way. So 100 this way. Now, if there is a 100 this way, you should, once you move here, you see a constant movement. Now, how would the movement change? Jump. Right? Movement jump by a constant movement. So now it's up or down? See, I heard different opinion. Up or down? No, it's up. Remember this diagram we draw? Okay, if there's a movement MO this way, it's going to be a delta M equals to negative MO. You go down MO. Now you have this way 100. So it should go up 100. Right? So it should go somewhere here. Is that correct? Okay, I'll explain in a second how you physically to explain why it's going up. All right, but according to our rule, you should go up 100. Okay, where were we here? What's the value here? This value here, supposed to be the area here, right? What's this area? 5 times 2. That's 10. So we were at negative 10 here. So this is negative 10. Now we go up 100. So where we end at? 90. So positive 90 here. Okay, now once across this point, okay, how would the M change then? Once you point across this point, now if you move, you're going to accumulate this area here, negative area. So you're going to go down, right? Okay, so from this point C to this point, let's call point D. How much does it change, the M change? 5 times, what's this distance? 3, okay, 15. So you should go down 15. Now start 90, go down 15. Where are you? 75, right? Okay, so go down 75. Okay, how is this curve here compared to this curve here? Are they supposed to be the same slope? Right, parallel. Because the slope is a magnitude of v. That's a constant. So it's supposed to be the same slope. So basically this constant moment just make it shift up. But keep this, after it will keep the same shape, same curve, or same slope. All right, so we end up with 75. Now what's next? What do you see? You see a distributed load, right? So that's this part. So you're going to continuously accumulate negative area. But at the beginning, you accumulate every inch is like 10. Then you accumulate more. So quicker, right? So the decreasing will be quicker and quicker. So what you get will be like this. So this will be like a curve like this. So parabolic. At the beginning, go down very slow. But at the very end, go down very fast. A parabolic curve. All right? So that will be the look like. Okay, although this look like continuous, but this part is linear. It's a line. This part is parabolic. Different shape. Yes? The curve should be concave like up, because Q is this way. Right? Whenever Q is pointing down, the curve always concave up. Yeah.
Will it ever be like your?
No, unless you have a Q that's pointing upward. Remember, the curvature is controlled by Q. So if you have a positive Q, that means going downward, you always have this concave curve this way. Unless Q change this way, then you have that. So what you have will be a curve like either this way or this way. So you can increase or decrease, but always concave up if the Q is this way. All right. Okay, any questions? Okay, now here is a quick explanation. You have a question?
Do we have to account for the moment of headache?
Yes. I'm not saying I end up at the 0. I didn't say that, right? So you end up whatever the value here. Let's say I end up here. Then that will be the RA. Actually, I didn't finish, right? So I left one part missing. So whatever you end up here, then this will move it back. That's the RA. I mean the MA. Will move it back to 0. All right. So what's the value of this point? This point, you can use equation of equilibrium, find out the MA, or you can just calculate this area. Now you know from 75 how much you go down further. Then you know where this point is, right? This end point where it is. Okay, anyone know how to calculate this area? Five plus 25, right? So that's 30. 30 times distance 5, so 150. Then divide by 2, so it's 75, right? So if you go down 75, where you end at? 0. Actually happened to be 0. Surprisingly, it happened to be 0, right? So therefore, you can conclude at this part, the reaction moment actually happened to be 0 because it's balanced out, right? This just accidentally happened to be 0. In general, they may not be 0. All right. Okay, any questions? Okay, let me quickly make a point here. why I'm jumping up here? Okay, according to the rule, you should jump up. That's mathematical rule there. Okay, physically, how would you understand it? Here's how I understand. Okay, let's say I'm coming from the left. I'm keep going, right? So let's see, look at this way. So I'm coming from the left. Oh, I see a counter movement. The movement is this way, right? Okay, this way. Now, this movement is going to bend this segment here. So if I have a segment, imagine I have this segment here. I'm bending this way. Now I'm bending this a positive one or negative one? Positive one. So I'm bending out, right? So this part is going to have a positive movement. Let's say I start 0. Somehow I see a movement bend this way. So I'm going to have a positive movement. That's why this should go up. That's how you understand it. Or you can just memorize, okay, clockwise, going up. Counterclockwise, going down. Which reaction? Well, what I'm saying is this counter movement. So for this part of the beam, if you look at, okay, here I apply this movement, you're going to bend this part of the beam upward. So that's applying a positive movement. That's why it's going up. That's just how I kind of physically say it there. Okay, any other questions? All right, last example here. So we have this overhanging beam. All right. So this part of the load is 16. Can you see it? I guess you can barely see it, right? But I'll explain. So this will be 16 here. This is 16. All right. So this is 3.2. And all the other, that's the value. Okay. Now the question is, okay, what's the maximum moment in this beam? So we need to draw the VM diagram, find out the maximum V, maximum M. Okay, now I want to draw the V here, right? But if I want to draw the V, immediately I see this RA. So I need to jump RA, but I don't know RA. So that's why step 0, I need to first find out what's RA and what's the RB. Any other reactions in this beam? Is there a reaction at point C, RC? No, it's free, right? It's overhanging there, stand free. So there's no RC, so don't try to calculate the RC there. All right? Okay, how can we find our RB? Equation of equilibrium, all right? So sigma Fy equals 0. All right, so we have RA plus RB equals to, this is a weird number. How about we change this number? Let me make this 2. Make this 2. Make this 2. Just easy to calculate. All right? So RA plus RB equal to P, right? So that's 3.2. That's the P value. Okay, then how about make this one 4? I like the easy to calculate, so this will be 4. All right, then plus generated by the Q. Okay, what's the force generated by Q? Q times this distance, so 16 times 2, right? So plus 16 times 2. Okay, so what's this value? 4 plus 32. So it will be 36, right? RA plus RB equals 36. Is that correct? 4 plus 32, so 36. All right, so we know RA, RB. Now, how can we find RA? Moment. Okay, moment to where? To point A. If you go moment to point A, you'll find what? RB. You won't find RA, you find RB. But that's okay, right? Okay, so let's say sigma moment to point A equals 0. All right, now write this equation. To point A, so you're going to have the Q generate 1, that is clockwise, right? So Q generate Q times 1, the moment. Is this correct? Okay, here's a common mistake often occurs. Whenever calculate the moment generated by distributed load, you have to calculate the force first. So the force is Q times 2. Q times the length 2. That is the force. And then force times the distance 1. That's the movement. Right? So you have to do 2 steps. Okay, so this is the first movement. Then what do you have? Then you have the RB times 4. Yeah, clockwise, you call negative. So this will be negative. Then this will be positive. Right? One is negative, one is positive. So you call one positive, not one. All right. Anything else? Should this equal 0 or the force on the very end, right? So you have this one, then you have this one is clockwise. So minus the P, that's 4, times what's the distance? 6 equals 0. Okay, from this equation, Q is 16. Can we find out RB? All right, anyone got the calculator? So 4RB equals to 32 plus 4 times 6, that's 24. So that equals to 66, or 56. Is that correct? Anyone got a calculator? Is it 56 correct? Yes. Okay, so RB is 56. Now we know this 56 here. Now what's RA? Oh, divided by 4. Yes. See, I got it wrong. All right, divided by 4. So what's RB? 14? Okay, so it's 14. Thank you. Otherwise, we're all wrong. Next, right? So it's critical get the RA-RB correct. Okay, RB is 14. What's RA? 22. Okay, so this will be 22 here. Now, can we draw the VM diagram? Yes, we have RA-RB. Everything ready, right? So this will be V, and then this will be M. Let's draw the V first. Start 0. Immediately, I say RA. So force should jump up 22. So here's 22. Right, so let's say here is 22. So I jump up 22. Then, maybe 22 is not enough. Let's say here is 22. All right, here's 22. Then what do you see? Once you pass this A point A. Now you see a distributed load, so it should be a steady decrease, right? So it should be steady decrease, so it will be decrease. Okay, now decrease by how much if you look at this point? Will be 16 times 2, 32. You need to decrease down by 32. So where you end at? Remember, this one is 22 here. So you end up at negative 10. Okay, so this will be negative 10 here. All right, so the line should be this way, straight line, right? Okay, once you pass this point, now you see nothing. So constant, 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 constant. Oh, I see a constant force. Go up by 14. Okay, so I end up here. This will be plus positive 4, right? Okay, now move over it. I see nothing, so constant, constant. Oh, here I see a constant force. Go down 4. Oh, back to 0. Oh, that's perfect. Start 0, back to 0. Okay. That's the V. Okay, now what about M? You start 0, right? Immediately you say a constant force. Jump? No, no jump, because that's force, right? Movement won't jump. So there will be no jump. So I go either this way or this way. Down or up? Up, because you're going to accumulate positive area here. So how can it be done? Now, how are you going to go up? Curved or straight line? Curved, because at the beginning you go up very quickly. See here, at one step you get this much area. Then next, here one step you get much less area. So at the beginning you go very steep, and then get gradually slow down. Okay, so should be something like this. Now, where is this peak? Right at where this v equals 0. So it should be here. So it should go like this. Keep going. Oh, here is the peak. Okay, once you cross this point, now you see you start accumulate negative area, right? So therefore you're going to go down. Oh, but once I reach this point here, now I don't see a change anymore. I have a constant accumulation now. So therefore should be straight line. But still accumulate negative area. So going down this way. Right? Okay, now what about this point here? Once I reach this point, what I see? I start accumulate positive area, right? So it should go up this way. Now, where is this point? You should calculate the areas, right? All this area on top of it. So you can calculate this point should be somewhere here. All right, so it's actually going this way. You go down here, and then this part you accumulate positive area, so go up, going back here. Now, can you tell which point is this? Where is this point? Okay, how much you go up from this point B to this point C? You're going up 4 times 2, 8. So where is point B? -8. Right? So this will be -8. Okay, so you can calculate from both sides, see if you meet at the -8 there. All right. Okay, homework. First, calculate what's the maximum value here. Okay, find out what's the value here. And then find out what's the value here. Okay, and this kind of question will be in the homework in the exam. So make sure you can calculate all these special points. What's the value? All right.